Hello everyone. Today we discuss contest 25 as the last contest of this season. I would say contest was very nice, not very difficult. So last problem unfortunately was probably too. I'm not sure why. It's not that difficult actually. No, it's kind of it's tricky, but nothing that difficult. We will see. Problem very different by the idea. So some problems are completely implementational. So you just implement what's written in the problem statement, but it's tricky. And some problems require some mathematics on the other hand. So you just pure mathematics, then you implement this and you get very short solution. Some problems are both. So we'll see. So let's see how I solved all the problems. Again, I pre-recorded myself solving all the problems. So we'll watch this recording and discuss what's happening. So the first problem, very straightforward. Just implement what's written from the statement. You have a bus, its capacity is M. You have groups of people. You put these groups in the bus. If the group extends the capacity of the bus, they wait for the next bus. So we just need to carefully implement this. So I have this. So C is capacity of my current bus. If capacity is not enough, then I wait for the next bus. Yes, I'll actually do it like this. So I just increase number of buses and make the capacity equal to M. Then I just decrease the capacity by number of people in the current group. That's it. So very straightforward, very short solution. Just the first problem to start the contest. I don't know, nothing really talk about in this problem. Let's go to problem B. Problem B is it's also very easy problem, but it's not about implementation, more about mathematical thinking. I try to solve this problem. Okay, first I misread the problem statement. That happens. So the problem is like this. So you have two properties. You have that number of people to the left is no less than A, and number of people to the right is not greater than B. Okay, so you will see. So first I kind of thought, so you have two constraints on number of people not less than B and number of people to the right not less than B. It would kind of make sense. So your possible position is the segment of elements. Yeah, but then I yeah, yes, at this point I read the first example and see that you don't have two in this case. So if you have in the left you have at least one and in the right you have at least one, then you have only one middle position. Yeah, so the answer should be two. So then I go back and yeah, so when I went back and looked what I missed in the problem statements, here you have no less, here you have no more. So basically you have two constraints from the same side. Here I'm doing it without paper. Normally in the contest I would do it using pen and paper. So how you usually do it during the contest, I will just show you. So I was just I tried to solve easy problems as fast as possible, so I skipped this part. But normally what I would do, so normally you just draw a picture, yeah. So you have n people, yeah. They have positions from 1, 2, 3, and so on n, yeah. So again, if you're not very comfortable solving this problem, it's just better to draw a picture which kind of explains what's going on. Now you draw all these conditions. So first condition, there is at no less than a people. So number of people here should be greater or equal than a. Yeah. What does it mean? So it means that your position, let's say position x, yeah. So if you have a people here, they have positions from 1, so 1, 2, and so on a, yeah. So number x should be greater or equal than a plus 1. Yeah. Second condition, it says a number of people to the right. Yeah, again, let's put it here, so it's not x. So I just mix the picture. Number of people here is no more, okay, no greater than b. Yeah. So if you have b people, they have positions from n minus 1 up to n minus b plus 1. Yeah. So this position is n minus b. Okay. So you have position n minus b or greater. Yeah. So x should be greater or equal to n minus b. Now we combine these two. So these two constraints are from the same side. We can combine them like this. So maximum of these two. And now you need to find how many positions you have. So you can position from here up to n. So you position from x up to n. Yeah. Okay. So the first position. Okay. So you have the leftmost position you have. So this is the leftmost position you have, and up to n. Yeah. So number position is n minus this and plus 1. Okay. So that's basically your answer. So that's how I would normally do it. So if I have enough time, I would draw this picture, write all these equations, carefully see what the equations I have, how I can combine them, so I don't have this plus minus 1 problems and so on. That's how I normally do it. Okay. So here I'm just I want to do it very fast. So what I'm doing instead, I just write the formula as I think it should look like. It should look something like this. Yeah. So should something like this. And then I will adjust these plus minus ones to pass both examples. Yeah. So I know it should be something like this. Yeah. Again, because I have n minus maximum. Yeah. So again, they have these two constraints. First constraint is kind of a, second constraint is kind of a minus b. Yeah. And then I will just adjust it to make sure it passes some simple tests. So I run this test, and I also run some. No, it's just in my head. I run some simple examples like n equals 1, a equals 0, and so on. So just small examples, just to make sure this formula satisfies all these small examples here. And then okay, yeah. So again, it's just some cheating way to solve problems like this, just to guess the formula. And sometimes during the contest, it's just easier to do. You just spend less time solving the problem if you just guess the formula instead of carefully make all these careful calculations to get this formula. Yeah. So problem C. Problem C, again, problem C is kind of classical problem about 2 pointers. Okay, it's some variation of this problem. So what we have two arrays. We want to combine pairs of the elements. So the difference in each pair is not greater than 1. Again, it's some variation of the problem. You may solve the same problem with. Okay, so the difference is not equal greater than 1 is not something special. You can make difference not greater than any constant actually even. So what is the idea? The idea is that you can assign elements in a sorted order. So if you take the boys, sort them in ascending order. Take the girls, sort them in ascending order. You can adjust them in this order. So you always can adjust like what was this number skill? So you can always adjust boy with the lower skill to the girl with the lower skill. Yeah, you never should adjust it, assign them like this. Yeah, so that's why you can basically use 2 pointers method. So I'm going here's my default implementation of the 2 pointers method. Okay, show me the code. Yeah. Okay, can you please release this selection? No, please. Yes. So that's my default implementation of the 2 pointers method. That's how I usually implement it. Again, I have full lesson on Codeforce about 2 pointers method. Very powerful technique. Just learn how to do it without any mistakes. So I usually implement like this. I have 2 loops. One loop moves 1 pointer, another loop this inner while loop moves the second pointer. Yeah. So I move 1 pointer with for loop. Just go from left to right. Yeah. And every time I move the second pointer to the leftmost accessible leftmost how it's called, so leftmost position that satisfies the condition. Yeah. So again, so I move the left pointer until I reach position which is greater or equal than a minus 1. See. And if I have position which greater or equal n minus 1 and it's also less or equal a plus 1, then I have a good position. I can make this pair. So I make this pair, move the right pointer. If if this is not satisfied, it means I cannot assign this boy to anyone. So I just skip him. Yeah? So that's it. This pretty classic implementation of two pointers method. Sometimes you have two pointers on a single array. Sometimes you have two pointers on two arrays like this. Difference is not actually that big. So you just implement this all the same thing. That's it. So it's again some variation of two pointers problem. Don't know what else to say. Let's go to the next problem. Problem D. Okay. Problem D is very easy. I don't know. We solved problem. We solved very similar problem, I believe, few contests ago. So you just need to make the array permutation. So you're given an array, you wanna change as less elements as possible and make the array some permutation. What you can do, again, multiple ways to do it. Idea is very simple. So you can, if you want to change as little elements as possible, you wanna keep as many elements as possible, right? So I wanna look at elements that I can keep. So I keep elements if they are in range from 1 to n, and they are not used with. So for each value from 1 to n, I can keep at most one element of this value. So I just keep again. So what I'm doing in this code, I'm going from left to right again. In this array z, I remember if I already have this element or not. So for each value, I remember if I already kept one element of this value. Again, I go from left to right. If the element is greater than n, I skip it. If the element is already used, I skipped it. Then I just remove it from the array. Yeah, not skip. I just remove it from the array. So I mark it -1. Yeah. If not, then I keep it in the array and mark it as used. Yeah. And then I need to fill the gaps. So I need to take all unused elements and fill all the gaps. So again, I do it using two pointers because I just solved two pointers problem. I just reuse it again. Again, multiple ways to do it. I just do it like this. So I go from left to right. Every time I pick the first unused element, so minimal unused element, put it in this position, move the pointer. Yeah. So that's it. So this code just fills all the gaps with all unused values. That's it. Again, there are many ways to solve this problem. This is just how I do it. Okay, now we end with the easy problems. Now we go to little bit more difficult problems. In the next problems, we actually need some intellect. So what's happening in problem E? In problem E, we need to find a segment such that we can change at most one element of the segment, so it becomes sorted. Okay, so let me show. So what I'm doing here? Can you please? Yeah. So what I'm doing here, so how do you solve problems like this? You draw a picture. So you have the array. So what we're looking for? We're looking for some segment. Yeah. In this segment, we will change at most one element. So at most one element. Let's say we change exactly one element. Yeah. Because if we change 0 element, we can take the first element and change it to itself. So let's say we always change one element. So let's pick the element which we changed. So imagine we changed this element. So this element was changed. Everything else should be the same. Yeah. Now, what do we know about these elements? So we know that this segment should be sorted after we do it. So this element should be less than this. This element should be less than this. Like this. So this element should be less than the new element we put here. So we replace this x with some, I don't know, y. Yeah. This should be less than this. This should be less than this. So again, so for this segment to be sorted, we need this part to be sorted and this part to be sorted. Yeah. Also, we need some relation between these two elements. Yeah. So let's say I have element which letters we don't use. Let's say elements. Let's say let's say C and D. I don't know why I skipped P. Okay. So C and D. Yeah? So what we know about this element C and D? We know that C and D must be such so we can put elements Y, yeah, in the middle of them. Yeah. they are all integers. So it's always possible to put integer between two elements if the difference is at least 2. Yeah. So that's what we need to check. So what I will do, I will check all possible positions where I can change the element. Then I will take this position, find the longest segment here, which is increasing, yeah, and find the longest increasing segment here. And then I will check if I can combine them. If I can combine them, and both these segments are sorted, then I can do it like this. I do this segment, replace x with this middle value between c and d, and replace this element. So now I have sorted segment like this. Okay, so that's the plan. So I will traverse over all different these x values and check if I can replace this element, and if I replace, then what is the longest sorted segment I can get. Okay, now how to find this longest segment? To find this longest segment, then for this position, I need to find maximal number of elements I can add, so I have increasing segment. It's easy to do. So what we have? So for the value, you need to find, and then greater, yeah? So this is maximal number of elements you can get of the increasing segment. So starting from this position, how long you can go to the right, so you still get increasing segment, yeah? You can easily do it by going from right to left and say, so here you have element 1. If you have, let's say, you have 2, then you have 3, then you have 4, then you have 5, then you have 6. Then at some point you have greater, yeah? Then starting from this position, you again have 1, yeah? So basically it's number of elements greater than us to the right, yeah? So just go from right to left and assign these values. And similarly here, you go from left to right and assign these values. It's okay. That's the classic part. I believe you know how to do it. The interesting part is checking this middle element. So I will start by calculating these values. So again, for each position, I will count how many elements to the left I can get. So I have sorted segment, and the longest sorted segment to the right. Yeah. Just like this. Yes, this should be n-2. I will fix it. Yeah, that's it basically. So I calculate longest segment to the left going from left to right, longest segment to the right going from right to left. Now the interesting part. So I iterate over this middle element. Here I think, so middle element should be not on the borders, yeah? But sometimes I want to actually change element on the border, yeah? So it's possible to, when you want to change element on the border, and here I think what will happen, it's different case. So you may have something like this. You may have a sorted segment, yeah? And then one element here, yeah? So one of the segments actually may be empty. Yeah. So you may have sorted segment plus one element. And it's always possible to take sorted segment and add one element if the sorted segment is not the whole array. Yeah. So if the sorted segment is the whole array, then the answer is just whole array. Yeah. Yeah. So I will just deal with this case after I deal with the general case. So here I check. So I look at two elements. So I check if the difference is at least 2, then I update my answer. So I take longest segment here, plus 1 in the middle. Yeah. Now I will deal with this special case. So the special case is I can take sort segment and plus 1 element. So I do this and I check in the end. So the answer shouldn't be greater than n. So if my whole array is sorted, the answer is n. Okay, here I try to find mistake. Okay, here this is mistake. Yeah. So this n-1 should be n-2. Okay, yes. Also here answer is 6. I'm not sure why the answer is 6. So I just check which part of the code produces answer 6. This part. So again, so instead of debugging step by step, I just print everything. Here I see it's 4. For 4, I have answer 7. It doesn't make any sense. It should be 7. It should be 5. So I just check what's wrong. Okay, thinking what the hell? Yeah. Okay. At some point I figured out that I misplaced L and R, and now it's working. So that's it. So this is the whole code for problem E. Tricky problem, not easy at all, but quite approachable. So no interesting, no special techniques used here, I believe. No, again, only special technique is to calculate this longest segment of increasing elements. Yeah, but again, it's just similar as calculating prefix sums or everything else. Yeah, or calculating like closest element to the right, yeah, for every position. So just go and remember the closest element, and you just move number of steps you can do. So if you can make one more step, you increase by one. Yes. If you cannot, then you have 0 steps. Yeah. Easy technique actually, but yeah. Problem itself is kind of tricky because of these special cases and stuff like that. And again, it's tricky. I believe it's the most difficult idea is that you check not for the segment but for the element you change. Yeah. So you're looking for the segment such that you can change one element. So instead of looking for segment, you track the element you change. And if you change the element, then for this changed element, you find the log of the segment. Yeah. Okay. That may be tricky. Let's go to the next problem. Problem F is pure implementation. I would say kind of boring implementation, but sometimes you have problems like this. Sometimes you just have problems when you need to do what's written in problem statement. Okay, and again, this program competition. So we're supposed to be programmers, so we're supposed to write programs. Yeah. So when a problem like this happens, the main part is not to be frustrated. So even if they have it's pretty short problem statement actually. Sometimes in some competitions there are problem statements of several sheets of paper, with very long specification of what you need to do in which cases and how you do it and so on. And it's just so frustrating to implement this. Here it's actually not. See, it's pretty just a small piece of code you need to implement. Just implement it. Just know how to program again. That's my advice, I believe. So if you feel not very comfortable solving problems like this, just you need more programming practice probably. So I believe it would be easier to do it in some Python or something like this. Yeah. Here I don't want to switch to Python in the middle of the contest. Here it's just easier to just implement it as it is. It's not that hard implementation. Yeah. So I just implement it as it is. So I just go from left to right. So that's how I usually split strings into words. So I just go from left to right, maintain the current word. And just when I see this comma or semicolon, I will just check if I have, if it is number, I put it in the first list. If it's not, I put it in the second list. So here I have special procedure which checks if it is number or not. Yes, I check about leading zeros. So if it's empty, it's not a number. If it starts with zero, here actually the 1 0 is considered as a number. So I will fix it later. Thank you for this example, by the way. Yeah, so you don't have leading zeros and except if you have a single zero. Just output the result. Here I added this comma in the beginning. And here I just remove it. So it's just easy for me to have this list comma separated with comma in the beginning. So here I just remove it. Yeah, same with the. Okay, here I forgot to add this character, so I split. Here I split my string into words, and I forgot to change the word. Yes, so when I see character which is not comma or semicolon, I need to add this character to the word. Yeah, it's just a lot of small mistakes. Yeah, here I need to check that single zero is a number. Yeah. Again, it's not very pretty problem, but it's okay problem. Yeah, it could be much worse. Yeah. It's okay problem. You just solve it and go forward. That's it. That's problem F. Okay, we move into the last problems. Problem G. Problem G is actually fun. I'm not sure what's the intended solution of problem G. Okay, I believe there are multiple ways to do it. I thought for some reason, first idea I got is that you can solve it using binary search. Now I think maybe it would be easier to solve it without binary search. I probably will read your solutions after that. But again, why I think about binary search, because a lot of problems of this form are much easier when you do it in terms of binary search. So what doing binary search? Binary search is basically reducing your problem from finding the smallest good value to just check if the value is good or not. Yeah, and usually it's much easier to check if the value is good or not than just finding the best value. Yeah. Here I just think that during this check I actually simulate the whole process, so it will be easy. But you'll see. So what I'm doing next? Yeah, here I think how would I check if so again I do binary search. So L and R are two pointers. Yeah, pointer L points to some bad timing. Yeah, so it's impossible to remove all boxes in -1 seconds. Yeah. In 0, maybe yes, we don't know. So if there are 0 boxes, maybe 0 is a good value. -1 is definitely bad value. Yeah. So R points to some good value. So I just checked that in total I have, yes, 10 power 9 boxes and 10 power 5 positions. So in total I have 10 power 14 boxes. Also I need to move at most. So 10 power 15 should be good enough. Yeah. So this value is definitely good. This value is definitely bad. Then I move. Then I take the middle pointer here, and just need to check if it is possible to remove all the boxes in this number of steps. Yeah. And what I will do, I will take all the students one by one and just simulate what the student does. Every student will just go from left to right and remove as many boxes as they probably can. Yeah. So I just take all the students and move them from left to right and just remove all boxes. Yes, now I actually think that binary search is more maybe the intended solution. I don't know how to do that binary search. Because, yes, I don't know how many students I need. Because when you move to the first pile, you don't know how many students you need to move next, yes? And if you move them next, you spend this time by moving. Yes, so yeah, probably binary search is the best solution here. Yeah, so what I'm doing here, I simulate job of every student. To make it fast, I remember the position of the first non-empty pile. So I take first non-empty pile, and for each here I iterate. So I rename this M to X. So X number of students, yeah, because I use M in the binary search. Yes, I don't want to mess up with my normal namings, so I just rename number of students. Number of students X. Yeah? So I take every student and just iterate over non-empty boxes and try to remove all the boxes from this pile if I can. So I just go from the first and see. So T is amount of time I already spent. Yeah. So while I have some extra time, I check. So if I have some non-empty pile, I check if I can remove the whole pile in the time limit. Then I remove all the whole pile. So you can remove and move next. So I remove the whole pile, move next to the next pile, and that's it. If I don't have enough time to remove all these boxes and move to the next pile, I just remove as many boxes as I can. So I just so I spend already t seconds and I have m seconds in total. So now I have extra m minus t seconds. So I spend them by removing m minus t boxes. Yeah. So I decrease number of babies and break. Yeah. So that's it. So that's how I simulate job of all students. And then in the end, I will check if all piles are empty, then I'm done. If it's okay, I move right pointer. If it's not okay, I move the left pointer. Here I forgot that I actually mess up this array A. So I need to save it and then restore it. Yeah. That's it. So okay, I have okay. Can you spot the integer overflow problem in this? Let me stop. So you can pause here and find the integer overflow problem in this. So I will get, okay, so just wait. So I move to the next problem like I usually do. So when I submit, I move to the next problem. But I will, yeah, I need to spend sometimes more because I actually, yeah, I have wrong answer test 49. Can you find the integer overflow problem in this code? I probably, yes, I need to force myself to use 64 in the integer everywhere. It's okay. It's okay. Every second contest I have integer overflow problems still. It's not good. Not good. Yeah. So every time it's a little bit embarrassing, yes. Again, what I'm doing usually, I just check all integers. So when I feel like it might be some integer overflow problems, I just find all ints in my code. So all 32 bits integers in my code and just check manually all of them. And usually at some point you find, so here I didn't do it. Yeah. This okay. I skipped this. Okay, this T should be long. Here I decided to double check all my guess. That's okay. I spent too much time looking for mistake where it should be. Uh, and because sometimes you feel like it must be integer overflow, but it's actually not. So I just check for some corner cases and stuff instead of just finding the integer overflow problem. Okay, I will find it eventually. Mm, yeah, spent too much time for that. Okay. How much time did I spend actually? Like 4 minutes between submits. Yeah, that's too much. Okay, but that's it. That's the whole code of the problem F or problem G actually. So it's not that difficult, I would say, but it is tricky problem. Yes. So you need to decide to use binary search. So now you move to the problem when you need to check if it is possible to remove all the boxes in this time. Yes, and then you think, okay, how I solve this problem? It's also not that easy. So okay, I believe there are multiple different solutions, but my solution is like this. So I just simulate every student by one. Every student greedily go from left to right and remove S box. You actually need to prove it's actually correct. You can use greedy approach, but okay, I will leave it to you as an exercise. Uh, okay, for me it's kind of it looks kind of obvious, but okay, if you want a formal proof, try to do it. It's good exercise of proving the greedy algorithms. Let me actually check your solutions before we move. Okay, you also use binary search. Makes sense. I go right to left. Oh, that's clever. So yes, I sometimes I forgot. Sometimes I forget about this trick that you can do right left. It may be yes, it's easier to do right from to left here. So you take the rightmost pile. You need to remove all elements from this pile. So you need to again to put some students here. So you can greedily put students to the last pile and remove from there. And then this, and then these students, if they have some extra time, they can remove some boxes on the way. So, okay, maybe not. It's maybe not that much simpler than my solution. Okay, my solution is not that complicated. So yeah, it's a nice trick. I forgot, but my solution is also, I believe, okay. Okay. Sometimes I like your solutions more than mine. Here, I think it's kind of the same. Yeah. But that's it. That's problem G. Let's move to the last problem. Problem H. So problem H is interesting. So you have okay. So actually multiple steps you need to do to solve this problem. so you have these strange values, these values, these values, and you need to reconstruct array A out of these values. So what I'm doing first, I'm trying to just figure out what's going on. Yeah. So I take these values and try to simulate the example. So in this example, you have, you know, the array looks like this, like 3, 5, 1, 1. And just, I just manually calculate these values and check that I understand how they are calculated. Yeah, I calculate some of these bitwise ANDs, some of these bitwise ORs, just manually calculate them and check that I understand again how they are calculated. Now, what I'm doing here, it's nice trick. So what I'm trying to do, I'm trying to get rid of bitwise operations because I have these formulas. They contain both bitwise operations and arithmetic operations, and it's kind of it's hard. It's very hard to mix them. Yeah. So what you usually want to do, you want to get rid of one type of these operations. Like here, I will get rid of bitwise operations by this trick. So if you calculate A or B plus A and B, you will get A plus B. Okay, if you never saw this formula before, it's okay. So idea of this formula is basically the same as with minimums and maximums. So if you take, let me show you. So if you take minimum of A and B and add maximum of A and B, you will have A plus B. Yeah. Well, because okay, smaller of them will be a minimum, greater of them will be maximum, but the sum will be the same. Yeah. So these two numbers will be either A or and B, or they will be in A. Yeah. And in both cases we have A plus B. Bitwise operations, they work kind of similar as maximum and minimum, but they kind of apply maximum and minimum to every bit. Yeah. So for every bit, so if you calculate AND, so you calculate minimum of bits. So if you have 0 and 1, you have 0, yes. If you have 0, 0, you have 0. If you have 1, 1, you have 1, yeah. Basically, for every bit, you take minimum value. And same for bitwise OR. Bitwise OR is basically maximum for every bit, yeah. So, similar logic applies to every bit. So for every bit, if you calculate AND plus OR, you will have just A plus B, yeah. And since every number is sum of the bits it composed, so again, if you have like number, I don't know, like let's say bitwise numbers, like number 5, yeah. So 5 is just 1, 0, 1 in binary, yeah. So it's just 1, 0, 0 in binary plus 1 in binary, yeah. Yep. So every number can be decomposed into powers of 2, basically. So into bits, yeah. So you have this bit plus this bit. And this sum can be decomposed into sum for every bit. Yeah, and for every bit you can use this formula, so you can use this formula. Yeah, so that's how I get this formula. So if you never saw it before, just okay, maybe you have some intuition to just guess this formula, or maybe just play with these values and see what you can do with these values. After you take this formula, actually everything else is pretty easy. So I just look at the sum of this. So here I see why I get this formula, because I see this value AI and A1, yes, and this value AY or N1, yes. I see these two values and think, okay, what if I calculate sum of them? Yes, I will get A plus B. Yeah? So sum of these numbers will be AI plus A1. Yeah. So if I calculate sum of all these, I will get A1, A1, AI, A1, A2, A3, and so on. Yeah. So the sum will be AI multiplied by N, because in every sum I have A1, AI. Yeah. Plus I will have sum of all values. So yeah. So this value will be sum of BI plus CI. Yeah. Let me finish this actually here. So again, what I want to say that the BI plus CI, yes, just because of these formulas, yeah. So this plus this will be AI plus A1 plus AI plus A2 plus and so on, yeah. So you combine these values, so it will be just AI multiplied by n. You have n sums, yeah? Plus you combine these values, yeah? It will be a1 plus a2 and so on. So it's just sum of all ai's, yeah? So you need this formula. Now, again, from this formula, we can deduce these values ai. So ai will be bi plus ci minus sum of ai divided by n. Yeah? But to calculate this, we need to know the sum of all elements. So you think, okay, how can I calculate sum of all elements? Should be easy, yeah? So I have these numbers, yeah? So if I just sum all of them, should be something good, yeah? So if you sum all bi plus ci, yeah, what you have? You have this, yeah, sum of all these elements. It will be just sum of all ai's multiplied by n. See? And this. So you have n elements equal to sum. So again, plus another sum of ai multiplied by n. Yeah. So it's just sum of all ai's multiplied by 2n. That's it. So that's how I will get sum of all elements. I will take this sum, it's easy to calculate, yeah, divided by 2n, and this number will be sum of all elements. So that's what we will do. That's what we will do. Well, let's see. So let's go step by step. So first calculate sum of all elements. Yeah. Okay, B and C. Yeah. Now, so again, this sum will be equal to sum of all elements multiplied by 2n. Yeah. So I just check if it's not divisible by 2n, then it's impossible. It's actually, you actually don't need this, I think now. So my final check will do it anyways. Yeah. But at this point, I didn't know about the last check. So now I know the sum of all elements. I can find the elements. Yeah. So check again. If it's not divisible, then it's -1. If it's not, I get this element. Yep. That's it. So now I know all the elements. Yes. So at this point, I thought it's okay. Yeah, so you saw that, yes. So I found all the good elements. But then I thought actually, okay, is it enough? So I found some solution, but I actually simplified the problem a lot, yeah? So I found solution for some reduced problem. So maybe this solution will not get me these values of B and C. Okay, sometimes it happens. Sometimes you think, okay, to make this true, I need to make this true, I need to make this true, I need to make this true, yeah? And then you solve the final problem, but then you need to go back and check that your final solution actually satisfies the initial constraint. Yeah, and here we actually need to do it. Yes, I just thought so. Yeah. Here I just check that I'm correct. Yeah. So again, I see that I always use sum bi plus ci. Yeah. So if I have the same sum here, the answer should be the same, but it doesn't work. Yeah, I should return -1 in this case. Yeah. So these numbers will not produce these sums. So I need to check. So again, I produce the only answer that can give me these sums. So I just need to check if this array produces these sums. To do this, you need to be able to calculate these sums efficiently. Let me show you how to do it. So what sums I need to calculate? So again, it's I believe it's pretty classical problem. Again, some variations of this problem are classical. So I need to calculate sum all elements. Okay, so bi should be equal to sum ai and aj. Yes, for all j from 1 to n. Yeah. Here I use, again, very classical trick. Again, what's the problem? I'm combining arithmetical operations and bitwise operations. It's hard to do. Yeah, so they mix very strangely. So what I'm doing instead, I want to get rid of bitwise operations. And here I use the following trick. I split these problems into bits. Yeah. So imagine imagine this AI. So each of this AI is 1 bit. So it's 0 or 1. Yeah. So if you have only zeros and ones here, so you solve problem only for single bit, then bitwise end actually equals to product. Yeah. So you need to calculate actually some. Oh, okay. I believe I solved each problem. Okay. Now I found actually easier solution, I believe. So if they are pronounced, then it should be something like this. It should be some AI op AJ. Yeah. From this, you can take this AI out here. Yeah. So you fill this AI multiply by sum of all AJ. Yeah. So that's what you need to do. Yeah. So you need to calculate sum of all bits, and then if your bit equals 1, then you add this sum to your result. And then I will just do the same for every bit and calculate sum for all bits, because again, every number can be split into individual bits. So I will solve problem for every individual bits and calculate sum of all the results. And the similar thing will happen to with OR. Bitwise OR basically the same. Yeah. So what I will do, I will calculate for every bit, I will calculate sum of these bits in all numbers. So this is CNT, I have numbers up to 10 power 9, so I have up to 30 bits. Look for all numbers, look for all bits. Yeah, just add this bit to the result. Yeah. So this is bit number j from number AI. See? So I calculate these sums. And now I produce the results. Okay, now I thought to put them in array, then I just check them one by one. You don't need to put them in array. So I go bit by, so I take a number, calculate sum for this number. Do this, I iterate over all bits. Yes, and do this. Yeah, that's basically it. So I take my bit, you see, this is my bit in position j, multiplied by number of bits in this array. That's it. And yes, then you need to move it left to corresponding position. So it's just bit, and then you move it left to put it in correct position. Multiply it by power of 2. Yeah. If it's incorrect, and then I will do the same for the. Okay, here I decided I need to check it first. It's good thing. So I checked that so this check actually works for the first example, so I don't make any mistakes here. Okay, here I think about some cool formula for OR, and okay, looking for this formula. So if I have 0 bit, then I have only CNT number of elements. If I have OR bit, then I have all n elements. Yeah, so it will be either CNT or all n bits. Yeah, so I do it like this: CNT plus n minus CC if I have bit here. Yeah. Okay, maybe not the best formula. Maybe you can do it better, but work good enough. It works. That's enough. So that's it. That was the last contest for this season. Thank you for being with me. See you.